then transform it by moving it around graphically in the coordinate plane. And we can do this in a variety of different ways. Let me sort of give you a very quick outline of the transformation, how it would look sort of in terms of a function notation. If you want a vertical translation, that means that you want to sort of shift things up. Then you just take the function and you add the appropriate amount to it. We notice that we're sort of taking the y values and adding to it, so therefore it's a vertical translation. If you want a horizontal translation, that's a translation in the x direction. We change the x to x minus a particular constant, and that's going to move things horizontally. If you want to stretch things vertically or compress them, so stretch things out or compress them in, then you put a scalar, a constant, right in front of the entire function. Multiply everything through by 2, and it gets twice as big. Multiply everything through by a third, it gets a third as small. If you want to do that horizontally with a horizontal stretch or compression, then we can actually do that by replacing x by 1 over b times x, where b is the amount of compression or stretch. And finally, if you wish to reflect on something, you can reflect on reflections, where we can reflect over the x-axis, the y-axis, or the x-axis. And if we want to reflect over the x-axis, we replace the function by negative f of x, switching all the y values to their opposite sign. And if you want to flip over the y-axis, then you take all the x's and you look at the opposite sign of those. Anyway, lots of information here. Let's just take a look at some examples to see this happening. Let's start off with this function f of x equals x cubed plus 1. And I want us to now write a rule for the function g of x, which is defined to be this transformation, f of x plus 5. So what is that? Well, it's going to actually be a vertical shift up. And so what would the rule be? The rule would be, well, I take f of x, which is just x cubed plus 1, and I'm supposed to just add 5. So when I do that, I see x cubed plus 6. So that's the rule. And let's see what the graph of that looks like. So here is the graph of x cubed plus 1. It's the function we start with. And you can see that this is just sort of the familiar cubic function. It's been already shifted up 1 unit. That's the starting function. And so now what do we do to get the g function? Well, what you can think of doing, since it's just a translation, is I can just sort of trace the function. I'm going to trace this in green. Kink! Little kink there. That's what the cubic is known for. That little kink right there. Little turn. And now what we do is we're going to raise it a total of 6 units from the origin, or 5 more units from where we are. So where we are, 5 more units up. 1, 2, 3, 4, 5. Again, so we start here. We go 1, 2, 3, 4, 5. And you can see that now represents the graph. The green represents the graph of the g of x function. All right, let's try another one together. Now let's make a horizontal shift, because we see the x's are changing. And so it's f of x minus 3. That means we're going to be shifting. And minus 3 means we're going to be shifting actually to the right, because it's x minus, and then whatever that value is, that's what we shift. It's x minus positive 3. Positive means to the right. So the rule for this would be g of x equals, now wherever I see an x, I'm going to replace it by x minus 3. So there I see an x right there. So I write x minus 3, quantity cubed, plus 1. All right, so what would the graph of this look like? Well, we start off with the same familiar image. And now I want to draw a version of this. I'm going to use purple this time. And here we go. And we got that little turning point. Here comes the little kink. Down. Okay, and now what I want to do is I want to take it right where it is, and I'm going to shift it 3 units, but in a horizontal direction. So what we're going to have here, let me move this over so you can really see this and enjoy it. 1, 2, 3. So you can see that now represents the graph of g of x, which is just the function f of x shifted 3 units over to the right. Now that we thinking about how different parameters impact the graph of different cubic functions, we can actually put these pieces together and actually graph really interesting cubic functions. Let's have a look and see if we can graph a very, very rough sketch of these cubic functions, and then, using some points, make an even more refined sketch of those same functions. Let's check them out. So, the name of the game here today is graph the cube root functions. The first one I want us to take a look at is g of x equals 3 times the cube root of x minus 2, and then plus 4. I look at this, and here's what I immediately think of. There are 3 things going on here. First of all, I've got a parent function, which is just the cube root of x function. But then, this tells me that I'm actually going to move it to the right. So this is going to be a horizontal shift to the right 2 units. And this plus 4, which I'm adding to the y's, means I'm going to raise up 4 units. So that's going to be easy. That's just a shift. That's pretty easy. So I've got a translation of 2 units to the right, and I've got 4 units up. But this 3 tells me about kind of the curvature. And since the 3 is a positive number, and it's bigger than 1, then I know this is going to be a vertical stretch. So it's going to kind of stretch out. So let's just try to draw a very rough sketch. And the way that I'll do it, just for fun, is I'm going to put in some of the earlier versions, and I'll put them in kind of dotted, just to kind of get us in the mood. So first I'm going to put in the parent function, cube root of x. So cube root of x looks like, oops, undo. I just can't make my pens write. You never get your pens that don't write, and you just wonder, why is it that they don't write? And I bet you it's going to be fixed in a second. You watch. Because if you try to write, if you try that, and then you shake it like this, you go like this, and like this, and like this, all of a sudden it works. Let's see if it works for me. You see, there it goes. So here's the usual one. Oh wait, I want to do it. After all that, I want to dot it, remember? Dot, 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 and then dot, 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 dot. That's that. So this is the y equals the cube root of x. Now what I want to do is I want to bring in these translations. So I'm going to move this center point, this origin, 2 units over. So 1, 2, and then 4 units up. 1, 2, 3, 4. So the exact same dotted curve, but now I want everything to kind of start over here. So it's going to look like this. I'll do my best here. This is just a sketch. And you see what I did? I try to kind of take this and move it over and move it up. I hope that came across. And this is y equals the cube root of x minus 2 and then plus 4. Now, what do I do now? Well, that 3 is now going to be a vertical stretch. So everything gets stretched, and so now it's just going to become more kind of extreme. And so I'll try to draw it right now. See if I can do it. Just more extreme, more extreme, more extreme. And then more extreme coming down. More extreme, more extreme, more extreme. Like that. So it looks something like that. So that's my guess of the graph. Now, in fact, we could plot some points by first taking the parent function points and finding the transformed versions of those points. And if you do that, you can get a little table of values. So here's the parent function values. And then here's the corresponding g function value. So you're just plotting points here. And if you now graph that, here is a very fancy, pretty version. Well, this one is very pretty, but you see it does kind of capture what I'm trying to do here. I tried here. You can definitely see that point is 2, 4, which is definitely 2, 4. So that point we nailed down. But the curvature and so forth and how it engages with the rest of the coordinate system, that requires the extra points. But we get a good sense of what the graph looks like. Terrific. Let's try another one together, actually. So this one is g of x equals the cube root of the quantity 1/2 times the quantity x minus 6, and then all minus 3. The first thing I notice is that there's an a here, but it's a little bit camouflaged, so let's immediately deal with that camouflage. I can pull that a out by pulling out the cube root of 1/2. So cube root of 1/2, that's the a, times the cube root of the rest, x minus 6, because the 1/2 is multiplied by all of that, and then I have a minus 3. Well, what do I see? This x minus 6 tells me that I'm going to move this to the right 6 units, so this is going to be a horizontal shift 6 units to the right. This minus 3 that I'm subtracting from all the y values means I'm going to drop it down, so it's going to be a vertical drop, so drop down 3 units. And this thing here, while it's positive, that number, if you work it out, it's actually less than 1. So in fact, what we see here is this is going to be something extreme. It's going to be a compression. And so what we see here is the following. We try to graph this ourselves right now live. I'm just going to do this very fast just to show you kind of what this might look like. First, I'm going to put in the parent function. Always start with the parent function. There's a quick sketch of the parent function. And then I'm going to move it over 6 and then up 3. So this point here is going to go over 6 and up 3. So let me just move in here. Here is, let's say, 6. Here is 3. So now I'm going to move everything up to there. So that's going to be about here, let's say. Just eyeballing this. Okay. And now we've got this compression. And the compression is going to be, yes, this. Nice and tight. Nice and tight. And what's the actual answer if you plot some points? Wait. The minus 3, I was supposed to drop this down by 3. Wait a second. See, everyone's getting all excited. This is supposed to be dropped down by 3. Minus 3. Why didn't you stop me? Where are you when I need you? All right, so let me tell you what we're going to do. I'm going to undo everything here. Watch this. I can go back in time. I can go back in time. And you're watching it go away. My mistakes just float away. And now what I can do is put in minus 3. That's what everyone wants. I could tell. You want that, because that's a minus 3. Remember, x minus 6 means I go this way, but the minus y goes, I go down here. So that's where I'm going to start. So everyone was right. You were absolutely right, and I just didn't listen to you, and that was not very nice. But no one said math is pretty. Actually, I did say math is pretty, so that was silly. Okay, now we've got the compression, the vertical compression by this number that's less than 1. So I think now we're on track, and check it out. Very tight. Very tight. That's my extremely rough sketch, just really with no numbers at all. If I were to actually look at numbers from the parent function and find the corresponding translations, so it's basically plot points, here's a bunch of points we could find, and if we take them and graph them, here's what we'd see. Let's compare that to the actual retail value, and you see that my picture is actually not bad. Do you see my picture in here? And notice that at 6, negative 3, here's 6, negative 3. There's that turning point. It's exactly what we have here. So my curve, I don't think, is that bad. And I have no points in there at all. But if you want a much more accurate picture, then actually plotting some transformed points from the parent function like this is actually really, really helpful. It will allow us to really solidify that beautiful curvature. And you can see it's a very subtle curvature, right? It's very subtle. And it's subtle because it's been compressed. Whereas in the other example, you see it's much more extreme because we had that 3 in front, which kind of actually stretched it vertically. So here's a stretched one, very pretty, but a little bit more extreme. Here's a much more subtle one because it's been compressed. Interesting to see the different variations of the cube root function. You got to be careful when you're translating up and down, right and left to make sure that everything is going okay. But as long as you think carefully, even a rough sketch will capture the essence of the curve. Have fun capturing the essence of the curves in your life, and I'll see you soon.